Welcome to the last lecture of week 15 of the course Fundamental of Econometrics, we were discussing chapter 7 regression diagnostic 4 model specification error. In the previous lecture, let me display all the model specification error issues. In the previous lecture, we were discussing that the classical linear regression assumed that the model are correctly specified. However, due to one of the given error issues, one or more than one given error issues, our model may not be correctly specified, and because of these model specification issues, our model results may not be trustful for policy making. So in the previous lecture, we discussed the first three issues of model specification errors. We did discuss that if we exclude a variable, which is very important, we call this a case of underfitting, and in this particular scenario, the parameters which we are going to estimate will be biased, in particularly if the excluded variable is linked with the remaining variable, and if it's not linked with the remaining variable, it will only bias the intercept term. However, in either case, the error term variances will not be correctly estimated, and it will reflect a problem in the T statistics and F statistics, and obviously the hypothesis testing mechanism, and finally the results will not be trustful. We also discussed the case when we include an irrelevant variable in our model, which we named the case of overfitting, and we saw that in that particular case the estimated parameters are still unbiased and consistent, and their variance are also small, but their variance are comparatively larger than the population parameters of the population model. However, we still can trust the results of the T statistics and the hypothesis testing mechanism. So we also discussed the Ramsey reset test and the Lagrange multiplier LM test for the model specification. Finally, we discussed the functional form, which is also an important requirement for linear regression model as per classical linear regression model assumptions. So in today's lecture, we are going to focus on the remaining 5 model specification error issues, and we are going to discuss that how this is going to affect the estimation and the results of our model. So to start with, the fourth model specification error issue is that the OLS, the classical linear regression model assumes that there should be no error of measurement in the regressant and regressors, or the dependent and independent variable should be free from error of measurements. However, if it's not the case, so what happens? So let me discuss this a bit more in detail. So till now, we were assuming implicitly that the variables which we have been using in our models and with which we were doing the practices, both the y and x variable have been measured without any kind of errors. Furthermore, it was not explicitly stated in assumption of classical linear regression model, but it's an implicit assumption that the value of the regressant and as well as the regressors are accurate. They are measured without any specification error. Now, there are a number of issues associated to it. When we say that they are free from error of measurement, it means we are not guessing the values of the variables. We are not doing any extrapolation or interpolation or doing any kind of rounding up that introduced a systematic changes in our data, or we are not recording anything with errors. So these are a lot of things to digest. So let me explain it one by one. By guess we mean that we are not trying to guess. If we can't measure it and we start guessing it, so that thing shouldn't be happening to measure x or y variables. Then interpolation refers to a case. Let's say we have a value of x variable for period x1 value, we have x2 value, then we have missing value, and then we have x3 value. So x5 value. So x3 and x4 are missing here, and interpolation techniques help us to find these values. And how they do that? Well, it is based on the simple assumption that as the values are moving between x1 x2, the same pattern is followed between x2 x3 and x3 and x4 and x4 and x5, and based on that, a linear relation between x2 and x5 is converted to interval x3 and x4. There is a formulas for that which do it. It's pretty much mechanical work. And then the extrapolation is slightly different. In that case, let's say we have the value of x1, x2, x3, x4. So we don't know the value of x5. So extrapolation helps us to find this value of x5. So that's the extrapolation. And then rounding up, you know it already, and recording errors you already know as well. So measurement error presume that x and y variables are measured without any of these kind of problems. So in practice, this is not true because of number of reasons, such as sometimes we have the respondent who do not want to respond to the questionnaire being given to them, or because of their hesitation, they don't want to share their personal information. Sometimes we have reporting errors as well, and in the country like Pakistan, people do fake data while filling the questionnaires. All these kind of issues may result in measurement errors of measuring variable y and x. In very simple words, it doesn't matter from where the error of measurement comes in, but error of measurement is a potentially troublesome problem for the regression analysis. So let me now discuss it one by one, that how an error of measurement in the dependent variable and then in the dependent variable do influence the regression analysis. So when there is error of measurement in the dependent variable or in the regressant, the OLS estimators are still unbiased. So the betas which we estimate from our regression analysis, they still remain unbiased, so that's nothing to worry about. Furthermore, the variances and standard error of OLS estimators are still unbiased when we have a dependent variable that having issues of error of measurement. Furthermore, the estimated variances and also the standard errors are larger compared to the case when we do not have the measurement error in the regressant or the dependent variable. So in simple word, it means if you have a case of error measurement in dependent variable and in another case without measurement error dependent variable, and if you run the model from both the dependent variables, the one which having measurement error will have a relatively larger standard error compared to the one which is free from these measurement errors. So in short term, if we look into the consequences, it's not so severe, or we can say it doesn't pose a very serious threat to the OLS estimation. Next, we talk about error of measurements in the independent variables or the regressor. So that's the case when we have the measurement error in the independent variable. So what happens in that case? In that case, when we have the dependent variable with error issues, if we do OLS estimation using these variables, the OLS estimator will be biased, they will be inconsistent. Furthermore, it's important to note that even error in a single explanatory variable can lead to biased and inconsistent estimates of the coefficient of other regressor in the model. So if you have even issue in one x variable out of the nx variables in your model, this one x variable potentially affect the all other variables in your model. Furthermore, it's not easy to establish the size and the direction of bias in the estimated coefficients. So not only one variable error, measurement error can cause the inconsistency in the estimates of the other regressors in the model. The size of the bias is not known, and we even can't find out the direction of the bias. So that's a very serious issue. Furthermore, the suggestion for solving the problem of measurement error is to use an instrumental variable or a proxy variable for the suspecting variable that having a problem of measurement error. So given the consequences, that's pretty serious, that the estimators become biased, inconsistent. Even one variable can spoil the all regression analysis you have been doing without having any track of the size or the direction of the bias it's introducing because of its measurement error. One potential solution to that is that instead of using that variable, use certain other variable instead of that variable which having issues of measurement errors. So that variables which you are substituting, which you are using as a substitute, is called proxy variable or an instrumental variable. However, instrumental variable can be used with certain minimum conditions. There are two major requirements to use any instrumental variables, and these are: first, the instrumental variable have to be very strongly correlated with the variable for which it is being used as a proxy. So it's like if you have one variable x, one that has a measurement issues, so you can replace it with another variable. Well, I will call it IV, instrumental variable IV. So you can replace x1 with IV variable only if these two are very strongly correlated. And secondly, the IV variable should not be correlated, should not be having measurement error. So it's like so it shouldn't have the measurement error, and it should not be correlated with the error term. So it's like IV variable can be used instead of the variable that having measurement issues, but this IV variable should be very strongly correlated with the variable which it is substituting, and it should not be correlated with the error term, or and it should not have any measurement error. So that may solve the problem of this measurement error. But the problem which it introduces is that finding such proxies are not easy. It's not easy to find a variable that's very strongly correlated with another variable, but at the same time it is free from measurement error, whereas the variable with which it is correlated is full of measurement errors. So that's not easy to find. Thus, we have to be very careful while collecting the primary data and making sure that some obvious we have to be making sure that the obvious errors are eliminated at the stage of collecting the data. So that was the case of error of measurement in independent variable. Now moving to the main slide. So we have covered that when there is error of measurement in the regressant or the regressors, what consequences it could have for our regression analysis. And we found out that the errors in the regressant is not that serious and its consequences are not that severe compared to the regressors measurement error, and apparently the regressors measurement errors are of more serious nature and could be solved through the usage of instrumental variable. Now we talk about the outliers in the data and how we can take care of outliers. So there are three associated concepts with outliers. These are outliers, leverage, and influence data. In principle, this is just one concept, but it's the kind of like different stages of one concept. So when we start with OLS method gives equal weight to every observation in the sample. It's like if you have a 20-year time series, so the first year value for observation has equal weight to the second year observation and the third year observation and the fourth year and subsequently up to the 20th. All these 20 observations will have exactly same weight. However, when we have certain kind of observation that's different than the rest of the sample observation, then we have the problem that OLS no more give equal weight to these observations. So it's a kind of like, let's say you have 20 observation and all these are within range of 10 to 20, but suddenly you have one observation that has a value of 1000. So now if you assign equal weight to all these observations, apparently that one observation which has a value of 1000 compared to the rest of the observation that have a range of 10 to 20, that one observation will be really something important and will be a problematic observation because it's different than the rest of the observation. So in very simple words, we call this one observation as a outlier, as a leverage, or as a influence point. These are the three concepts which I'm now going to explain. So outliers refers to in context of regression analysis an observation for which we have a very large residual comparison with the rest of observations. So let's say you fit a regression model, you obtained your residuals, and then when you were looking at the residual, suddenly you find that one or few values of the residual are quite large compared to the rest of the residual values. So in order to understand the logic that why it is a problem, think of the calculation of the residual value. We know that the residual value is obtained by subtracting yi forecasted from the original value. So yi forecasted being subtracted from the original value give us the error term or ui. So what does it mean when this value is large? It means that the model, the value it is predicting is much far smaller or larger compared to the original value. Or in other words, if I put it in more simple word, the regression analysis are run on averages. So if a value is very much larger compared to the rest of the values in the sample, so when the regression model forecasts that value, it will be forecasting a value closer to the average, but since that particular value is far away from the average, so their error term would be higher. So that's a way of knowing the outliers in your data. It will have a larger residual value. Then we have the concept of a leverage. So in observation, that is said to be a leverage if it is disproportionately distant from the bulk of sample observation. In this case, such observations can pull the regression line toward itself, which may distort the slope of regression line. So what does this whole statement mean? It means that when you have one observation, as I was giving the example, that out of 10 there is one, out of 20 there is one observation which value is very high, very large compared to the rest of the 19 values. So if this particular value drag the entire sample observations toward itself, or the regression line toward itself, we call this observation, or this particular observation, we call it the leverage, or we say that it's going to distort the regression line. I can give you a much simpler example of that. For example, if in a class of 100 students, or let's say 50 student class, if every student, if all 99.9% students score between or up to 70% during the entire semester, but only one student score 100%. So we can think of this 100% marks as an outlier or as an leverage. Why? Because this one single observation is going to drag the average from 70 towards 80 or plus. So that's why we can call this a leverage. And we say that this may, if we have such kind of observation in our regression analysis, it is going to drag or pull the regression towards itself and thus distort the slope of the regression line. So when a leveraged observation actually pull the regression line toward itself, we call it influential point. And the influential point consideration in the data is important, because if we keep these points in our data and if we exclude these points from our data and we do the regression analysis, in both cases the result will be dramatically different. So in such scenarios, the recommended policies is that we should be aware of having outliers in our data, and if these outliers are leverage or influential points, and if these are going to affect our results. So the traditional approach is to use the error term and see if it is display any 4 values for the residual. So that's the step to identify if there is a outliers in our data. So once we know that there is an outliers in our data, and if there is an observation that has a huge residual value, one way to solve the problem of that would be to drop that residual from the analysis. Many researchers do report the results with and without the outliers value, and thus make their research findings and share with the people. However, the dropping or keeping a outlier values depends on the research question. It may be noted that there are some tests for testing if a particular observation or observations are outliers or not, but however I will exclude that from discussion at this point in time. So let me go back to my original slide. So we were discussing issue number 4 and 5 for model specification errors. We have covered that if there are errors of measurement in regression and regressors, what happens to the regression analysis. We also saw that if there is an outliers in our data, what implication it could have for our regression analysis. Now we move to the 6th model specification error issues, which is the probability distribution of the error term is well specified. So let me go there. Probability distribution of the error term. So when we consider the classical linear model, classical linear regression model, that's the restrictive model, which has just 7 assumptions for the insurance of blue parameter. However, there is an extended version of this classical linear regression model, which we call classical normal linear regression model. So the word normal is added to it. Classical normal linear regression model. This is an extension of the traditional classical linear regression model, and since it's an extended version of it, so obviously there are more assumptions to classical normal linear regression model. So the classical normal linear regression model assume that the error term of the regression model should be normally distributed. So that's the prereq, or that's the assumption of classical normal regression model. This assumption is very much important if the sample size is relatively small. So for small sample size, it's important to have this assumption valid so that we can trust our results for T and F statistics, because these are based on normality assumption. So if error terms are normal or not normal, we can check that through a test which we call Jagbera or JB test for normality. This test shouldn't be new to you people, because we have been using that without explicitly discussing it in too much detail. So today we are going to discuss it a bit more in detail. Jagbera or JB test is for large sample. It's for large sample test. Their test statistic is given as JB equal to n within bracket s square over 6 plus k minus 3 whole square divided by 24, where n is the sample size, s is the skewness coefficient, and k is the kurtosis coefficient. Now I'm not sure if you can recall what is meant by skewness and kurtosis. Just to refresh your memories on that, I have put two small graphs here to explain this concept. So first I will talk about the skewness. Skewness refers to the symmetry of the distribution. So for a normal distribution, we know that it's a perfectly symmetric distribution. The mean is in the middle, and the left and right tail of the normal distribution is perfectly mirror image of one another, and it's 50% on the right side and 50% on the left side. And then you can think of something different than the normal distribution. So the skewness is measured with what we call skewness coefficient. It's not the right time to discuss the formulas of the skewness coefficient. However, we can say that the skewness coefficient values is 0 for a normal distribution. Otherwise, it could be positive or negative values. As you can see here in these three graphs, the middle graph is for normal distribution, where skewness coefficient is 0, and then for the positive skewness and for the negative skewness, you can see accordingly the left side of the normal distribution and the right side of the tail for the normal distribution. Similarly, the kurtosis refers to the peakness of the distribution. So if it's a kind of like the spread and the peakness, so kurtosis is measured through kurtosis coefficient, and its value is equal to 3 for a normal distribution, and it is called mesocratic. And if the kurtosis coefficient values is greater than 3, it's called leptocratic, and if its value is less than 3, it's called platicrotic. Now, if we use the normal distribution values as in skewness, if we put 0, and for kurtosis we put the value 3, we get 0 from here, and we get 0 from here, and that's what I have written. For normal distribution, skewness and kurtosis coefficient respectively are 0 and 3. So in that case, the Jagbera statistics is 0. So when we get GB 0, it's clearly reflecting that the underlying if the error term having GB value 0, so it means that the errors are normally distributed. However, sometime you may not have the value of 0, instead it may be close to 0. So in that case, you will always be in doubt that if it is normally distributed or not. So for that purpose, it has been shown that well, we know that already that error terms are not observable, so we use the forecasted value as a proxy. So if we need to test if GB value is actually equal to 0 or not, we know that from statistician that JB values follows chi-square distribution with 2 degree of freedom. It's because of 2 degree of freedom is because there is 2 restriction, that is the skewness and kurtosis coefficient being set to 0 and 3 respectively. So chi-square distribution with 2 degree of freedom is used to test the GB value being equal to 0 or not equal to 0. If the test statistic value, chi-square value with 2 degree of freedom reject the hypothesis, that means that the error term is normal, otherwise it's not. So that's the JB or Jagpera test for normality. Then let me move to the main slide again, and now we have covered the 3 more issues of model specification errors. In total it makes it 6. Now we move to the 7th requirement or 7th issues of model specification error, which says what happens if the regressors are stochastic. Regressors refers to the explanatory variables values, x values. So the classical linear regression model assume that these are the dependent variable or the regressant are random, but the regressor or the explanatory variable are non-stochastic or fixed. That is, we keep the value of the regressor fixed and draw several random sample of the dependent variable. So this is the assumption of classical linear regression model. For reference, you can switch back to the lecture where we discussed the assumption of classical linear regression model. There was one assumption which I did explain through the help of example of income and consumption, in which we have seen that the value of x is fixed and y value is observed for fixed value of x. So this implies that we observe random sample of dependent variable for given fixed value of x variable. So if this assumption normally do hold for, this assumption of fixed value of x do hold for number of economic situation, however it does not hold true for all kind of economic data. So in another word, we have both the dependent and independent variable drawn randomly from the population. So this is the case of stochastic or random regressor. Given that the consequences of x variable being random is not so severe for the OLS estimation, so we are not too much worried about this phenomenon. So in the bottom line is that although x variables are assumed to be fixed while the y variable are assumed to be random, in practice we have both x and y being random most of the time, and it has no major consequences for the OLS estimator, so we can just live with this violation of the OLS estimator. So let me go back to the last model specification error, which is the simultaneous equation problem or the simultaneity bias. So what is the simultaneity problem or simultaneity bias? Let me start with a very simple example of a Keynesian economics. We says that in Keynesian economics that y is equal to c plus I plus g plus nx or net export. So this is the classical, this is the Keynesian or you can say this is the 4-sector economy model in which output is function of consumption, investment, government spending and net exports. Then we also have a model further that consumption is being function of consumption and income, And here you can see here, if we have to estimate this model, on one hand we have also YD, function of income or output. So here I have wrote three equations. In the first equation, y is function of four variables, and then one of these four variables I have again function of the main dependent variable. So the point I want to make it that till now we were just looking at only this equation, that y is function of number of x variable. There was always one way direction of the relationship, that y is always dependent on x variable. However, in real world we may have a situation where this relationship may be two-way, that y is dependent on c and then c in return is dependent on y. So it's a two-way moment. So there are many situations where unidirectional relationship between y and x cannot be maintained, since some x affect y, but in turn y also affect one or more x. And in another word, there may be a feedback relation between the y and x variables, and as we can see here that y or output is function of consumption, investment, government spending and net exports, and then in return consumption is function of income. So it's a kind of like two-way mechanism, or two-way relationship is working between the dependent and independent variable. So this is called simultaneous equation regression models, and while estimating these models we have to take care of that feedback relation between y and x variable. So we have to take care of both kind of bidirectional relationship between y and x. We just can't estimate one of these equations while ignoring the remaining equation in the model. So there are two major kind of variables associated with these kind of models. The first one is called endogenous variables, or the variables that are determined within these models, and then we have the exogenous variables, or the variables that has been determined outside of the model. And sometimes these exogenous variables are also called predetermined variables, because their values are independently fixed. Or for example, when we think about introducing tax here, which the government collect, so in that case the tax would be fixed by the government, so it's a predetermined fixed value of the variable. So these models cannot be estimated through ordinary least square method, because the ordinary least square method is good for only unidirectional relationship between y and x variable. To keep in context the feedback relation as well from x to y, we have to use different estimation methodologies. The most useful for simultaneous equation are method of indirect least square, or method of two-stage least square. In this methodology, these models are first converted to what we call the reduced form equations, and then these reduced form equations are estimated through ordinary least square method. So since the application of this methodology is beyond the scope of this course, so I will skip that and I will switch back to my original model, my original slide. So coming back to the introduction of main slide, the model specification error. So till now we have covered all the 8 specification errors. So to sum it up, we started with classical linear regression model assumption that the model which are going to be estimated through OLS under the assumption of classical linear regression model should be correctly specified. And then we said that the specification, correct specification refers to one or more issues, 8 issues, one or more of the 8 given issues, and then we discussed in detail all that 8 issues, starting with the inclusion of all important variable, and do not including any or not including any irrelevant variable. We also discussed the consequences of having these issues and how we can test for it. Then we talked about the functional form of the model, that it should be correctly done. We very briefly discussed that. Then in today's lecture, we cover the remaining 5 from 4 to 8, and that covers the no error of measurement in the regressor and regressors, the issue of outliers in the data and how to take care of it, and then the probability distribution of the error term should be being normal, and then the regressor being stochastic or fixed, and if it has any consequences for the regression model. Finally, we discussed the simultaneity equation problem that summarize the idea is that it's sometimes we have a phenomena that has that cannot be defined through unidirectional relationships. So in that case, we cannot use ordinary least square method. Instead, we have to consider a system of equation which is called simultaneous equation, and for that estimation we have to use indirect least square or two-stage least square method. So with that, we covered the model specification errors. Thank you very much for your patience and being with me for a longer period of time to cover these topics. I hope you learn from this session, and I hope I see you in my next lecture. If you like my videos, please do subscribe my channel, and I see you in next lecture. Thank you.